Good evening, everyone. Welcome to such a large audience for our special Christmas lecture this year. And welcome to all of those who are attending online. Very happy to introduce tonight's meeting. And we are very honoured to have with us Conrad Wolfram, who's the European co-founder and CEO of Wolfram Research. Probably doesn't need much introduction from me, and whatever is needed, he's probably going to do himself. So I will hand you over to Conrad now and not steal his thunder.
That's kind, particularly in its brevity, which is, I think, is a mark of kindness. Anyway, in my view. So I've got rather a lot of different things to say, but the tie-up here is I want to think about the trajectory of computation as an idea and how it, I think, aligns in the past, present, and will do in the future with society. And so we'll see how this goes. I also have various bits of demos and things that may or may not pan out as planned, and I'll try and go those through. So, you know, we take computation, the idea that you have a process by which you can compute deliberate results, and now things that seem less deliberate, as a kind of, you know, we're so used to it now, it seems obvious. But it's an incredibly powerful idea that I don't think was obvious until pretty recent times. And I guess one of the questions I have is sort of, where are we on that trajectory? How much further, I mean, where are we on the direct trajectory of where we can go with this powerful idea of computation? Are we near the beginning? Are we kind of near, you know, we're just turning over the things that kind of, you know, near the end game? And I want to sort of explore that a little bit and think about some of the experience we've had over the last few decades. So really, you know, this talk is really sort of three bits, in a sense, intermingled. It's, you know, our interaction with computation so far, and the comparison I'm going to come back to a few times is with the rise of electricity in the 19th century, which I think is a sort of interesting previous historical complete revolution in sort of basic capability. Obviously one that has been, you know, required for this revolution. AI and what we think that is and means, and also the future of sort of computation intelligence for humans alongside the machines. What have we been doing? Well, it's 36 years actually since, I guess it's 36 and a half years since Mathematica was released in 1988. It's the 23rd of June, which we discovered when Wolfram Alpha was born, was Alan Turing's birthday. But that was it turned out that was by accident. And basically, we've been building elements of this computational space out since in that time. I think one thing that's interesting in that time is how it's become apparently a less specialist endeavor in the world. You know, 36 years ago, things were very specialist. And it was the idea of building a company that was based on math, or I guess we're in the UK, so it should be maths, was, you know, I guess it was actually, I noticed the one below was maths, but anyway, there we go. You know, the idea that you could base a company to do things on maths was crazy. Like, it's not something you could obviously sort of get investment for, not that we got investment. And, you know, it's sort of like now maths, not necessarily called maths, computation is everywhere. And we've gone from this sort of era where there's a specialist little group that thinks about things in a computational way to everyone to some extent basing decisions on computation. They may not realize they're doing that, but they're doing it far more than they were 35, 36 years ago. So, I mean, a typical thing, you know, as you know, from a long time ago that would sort of wow people is, I don't know, I don't know what integral I'm going to do here, but, you know, something. And, you know, the fact that, what am I doing here? It shows that I'm really, hang on just a moment. No, something's gone wrong here. Escape. let's do that. I don't know why something is going completely. It's this time of what? Well, that's not going to work. It needs an argument, as it correctly says. That's what I wanted to do. Yeah. Okay. So now I'm waking up finally. Okay. That shows my ignorance of this time. It's too much playing with things writing code for me. Anyway, so this was very exciting 36 years ago. The fact that a computer could do this, even though computers had in fact been able to do this before. If you obviously this was not for everyone. Although it's surprising how many calculus students in the US need to do this, although they know not why. So I guess that's still more every day than you might think. What I want to do here, hopefully. Oh no, that's not a great start. Let me wait for the program to run. Okay, right. Continue waiting. Right. Let's see if this demo works. So, now it would be very common to, oh gosh, okay, something is definitely hiccup. This is very bad at this stage in the talk for this to happen. Now I have an idea of why this might have happened. Yes, no, I should be in the right version of Mathematica here. Okay, well, that's not great, but let's try once again just to see if we can get this working. I was going to show a very simple demo of looking at my face and trying to guess my age, which would be a very standard thing you do nowadays. And for some reason, this is oh, there we go. Something's happening, but extremely slowly. Like a mollusk has infected my machine or something. There we go. Okay, there we are, but I don't know why it was so unbelievably slow. Okay, so it's being quite nice to me. It's claiming I'm like, it's not particularly. I think its background is and facial expression we could try as well, and we'll see whether that works. It's a bit variable at the moment. I think that's probably quite enough of that. Anyway, my point is that the idea that you can analyze an image, get some result out, you can potentially do it on a little computer and things like that. That seems pretty everyday now. Even 10 or 15 years ago, that was a much more exciting sort of demo to do. So that's sort of where we've gone. I think I'm going to sort of say up to the end of 2022, high-level computation had sort of got everywhere already. And I sort of break it into three different places that I think are interesting. So there's stuff where it's kind of intrinsic. Maths, physics is not intrinsic, but it's very much been present in physics as a sort of idea underlying it, and things like accounting, which kind of grew it in maths. Then obviously there's middle column, things that exist because of computation. I mean, programming, data science, things that really are newly conceived. I'm actually in many ways very interested in this right column, which is things that have existed, for a long time, forever, but now are have a computational version of them in a sense. So the idea that you could do, I don't know, a lot of computation in marketing and business. It's funny. I went to some conference, I forget what it's called, but it's basically a sort of marketing conference thing. And when I went 5 years later, all the people had turned into sort of maths, computer science people from being advertising people. Right, so that's a sort of shift that happened maybe 5 or 10 years ago, where the data science was very, very important in that area of life. And so history and archaeology has become much more lots of image processing and all sorts of things, which just didn't exist. So this idea that computation sort of infused everything at some level, I think has very much happened over these last 36 or so years. And demo 2, let's see if this works. If I, for example, just type in I'm going to just pick a sequence length here, something like, a sequence I hope it's in the human genome, I can actually go and look that up. And hopefully, if my machine is not totally mollusked, what is it doing? Okay, oh my gosh, okay, well, there was only one place apparently in the human genome where that particular sequence appears. But the fact that I can ask that question and get an answer in a few seconds on a laptop computer is amazing. I mean, I think the Human Genome Sequencing Project only started in the Clinton era, if I remember correctly. And the fact that that's now kind of available like this as a computational query about some piece of biology is pretty interesting. This was a blog post a colleague of mine did about, I guess, sort of sentiment analysis in, Jack and the Beast and everything else, and sentiments of the different characters through the book. Again, you'd never have thought of sort of looking at things in that way. So that takes us to the end of 2022. What's happened since sort of early 2023? I think we've got this high-level computation everywhere is now potentially sort of accessible to everyone in all fields. I mean, at least that's the trajectory one sort of hopes that the latest tranche of AI may help with. And so I suppose in some ways I think of sort of LLMs, ChatGPT and so forth as a major new bridge between sort of, in a sense, the human world where we talk in normal human language and things like that, and this sort of more abstract computational world. I think how those bridges play out is pretty interesting. So it's worth sort of looking at what actually seemed to have worked well till the end of 2022 in computation. So there were these traditional computational domains that were pretty well attacked, physics being a very obvious one, and sort of scaling up ideas and ways of doing things that had happened and building huge new algorithm sets around those. And sort of things that seemed very deliberate models, although, of course, we had machine learning for a long time by then. There's sort of this thing where, and we still have this problem majorly, we have simple to specify types of data. And we struggle, I think, a lot, and this will play out, I think, over the next few years, with data that's kind of hard to specify. And so we tend to jump to these numbers that are rather simplistic and don't represent the situation very well and compute from them because we can do that computation. So we do well with simple to specify questions of data where you can just put a number and the number is sort of easy to work from. I think we do rather badly with sort of fuzzy questioning, although that's getting much better potentially. Sort of how we communicate ideas in computation hasn't gone terribly well some of the time. It's very limited to whom that communication works well. If you look in the pandemic, for example, where people, there was an attempt to communicate to the general public risk ideas and things like this. It was pretty hard going. I think it was a mixture of how the communication was done, although lots of things were attempted, were quite sensible, and understanding on the human end that was pretty limited. And so these are things that I think, these are many things that really had done rather badly till the end of 2022. I think the thing now, so my argument is a lot of those things are moving forwards. We've supercharged some of the change from those things. And I think we've got a long way to run in where computation can go. And I think sort of comparison with electricity, and this started off because I was giving a talk in the Royal Institution in 2021, which was 200 years since Faraday first ran his motor there. And so this got me thinking about this comparison. It's sort of like, there are various phases of what happened, I think, with electricity. Firstly, there were various effects that were known and things that were done individually. And then these got put together, particularly by Faraday and subsequently by Maxwell, into a sort of global picture of where, this idea of electricity and what it could do. And that sort of systematization, it then got people thinking. There was sort of, initially you try running the things that you'd done before and sort of way you've done it before, but you do it and sort of do it with electricity. And then you say, well, actually, there's a completely different way to think about things. Now we can do things electrically. We can sort of change our mindset. And at some point, you think it's assumed. It's like electricity is around. I've come to this room. I assume there's electricity. Plug my laptop in. It's all very systematized. I know what the plugs look like. They're even systematized more or less around the world, at least into a few different types. And that has a huge power when you get this kind of systematization, so you can assume various sorts of things. And at some point, it gets deployed on everything. So it's kind of like you get electric toothbrushes. It's like, well, you didn't really need to make the toothbrush electric, but you could. It was easy. It's quite hard to find these windows on cars these days, right? Because you just put an electric motor in. And so where are we at if you look at the trajectory of electricity? What date would you pick? I don't know, 1860 if we're comparing with computation. We're at the sort of level of maybe about 1860 in terms of the trajectory of electricity. So we're maybe, 150 plus years later with computation. So I think my argument here is we've sort of got a long way to go in terms of things that will happen with computation, although it may go rather faster than it did in terms of electricity because the world tends to move a bit faster. So what have we been trying to do? I suppose what we've been trying to do, I mean, I'm not sure I would have claimed this 20 or 30 years ago. It's like you look back and you make some grand claim as to what you're trying to do. But I think what we've been trying to do is inject computation everywhere because we kind of believe in the power of computation. And why are we doing this? Because computation is a fantastic way, if you like, to make decisions about things. And it might be decisions because you're trying to work out some piece of mathematics, or it might be just decisions about, life. And you can talk about the decision in English, but actually, if you can model it and do data science on it, whatever it is you're doing, you can potentially come up with a much better, more accurate, more precise description, better, better prediction, and so forth. And so what we've really been trying to do is build an architecture. So in a sense, you can represent any computational idea cleanly and systematically with the other ideas. Because as I mentioned for electricity, I think there's a huge amount of power in being able to piece all these apparently disparate things together. I mean, it's kind of like the general power of abstraction, and we're trying to cause this abstraction for computation in general. But it's interesting, like when LLMs came out a couple of years ago en masse, it was extremely easy for us to build in sort of more of that kind of computational idea straight into what we do, because it all fits very nicely with how we structure our language. So we can just easily add these sorts of pieces of high-level functionality, and they kind of interoperate with everything. And, all sorts of different elements here, not just explicit mathematical functions put together. So what we've been trying to do is build this sort of ultimate infrastructure to be able to deliver ubiquitous computation. So wherever you can meaningfully use computation, we hopefully have built some nice piece of structure to allow that to happen efficiently. And, a bit like sort of, Maxwell tried to do this and did it very successfully for electricity, where you have a very nice structure to piece everything into. So just back to what I mean by that, so for example, everything in our language is a symbolic expression. So if you look here, this is sort of like different elements, if you like, on the left, as you might think of them, piece of maths and its typesetting. And here it is in its symbolic representation on the right. And you can do the same with data or graphs or images or documents. So this document I'm in now is simply a symbolic expression that represents the document. It could be a differential equation. It just happens to be a document. And it's represented that way. We think of those all in the same kind of structure. So then you can, it's a neural net or it's a program and it may be represented differently, but there it is as a symbolic representation. So that's kind of the underlying glue, in a sense, what we're doing. We struggle a little bit to explain, what the Wolfram language was trying to do, because it's really three things. That's why there are three wolves here. It's sort of like, it's a programming language. So meaning you can instruct the computer to do something, and there's a language to tell the computer what to do. But we're also trying to make this representation for all of computation. So you can neatly write down an idea, and it might not be you particularly doing that just so that the computer can work it out. It might be you just want to do it because you want to represent that idea to another human. But there's a way to represent those ideas that's quite clean. And in a sense, you can also use that as sort of communication language. It's funny because sometimes in Wolfram, we communicate with other people. Just is this what you mean you're asking for? Here's a function. Does this mean, is this what you mean, right? Just tell me, does this function represent what you were just saying in English, right? Because it's just better to write it down in an abstract way if the other people can also speak that language just as humans, because we have a neat way of writing those things down. So one of the ideas we've had is to sort of put it this way, multi-paradigm everything. So don't lock the method in with the concept, I suppose is one way to put this. Don't pick the method before you know what you're trying to do. It's a common problem. I mean, I like it when you see ads. I'm interested in the machine learning specialist. Oh, really? So why do you know that the problem you're doing is necessarily a machine learning problem that you should attack with machine learning? Maybe, but maybe there are other approaches that you might use. So why is it a machine learning specialist you want, right? Don't pick the method first. And so, for example, early on, I mean, this seems very uncontentious now, but early on, we had like a numerical differential equation solver, and you just asked it to solve a differential equation. It's like, but you mean you're not specifying the method up front? Well, no, because the person who wants to solve the differential equation may not know as much about the methods, whether it's the Runge-Kutta-45 method or whatever. They may not know that because they're a user of it, not necessarily the programmer of the thing. So you need to separate sort of what you're trying to do from how it's being done and try and automate that as much as possible. Now, sometimes the automation doesn't work well. So there's a sort of funny interplay as things get automated, of trying to get them more automated, sort of more effectively automated, and who can actually use that effectively and knowing when it's going to break. Except, as I say, multi-paradigm everything. Have many methods, many ways to do lots of things that you represent, but have one representation that's very common to everything, so you can kind of cross these boundaries all the time. And I suppose, as I was just trying to show, if you were trying to pick the areas that we're trying to represent, this is very rough. It would be sort of data algorithms, linguistics, notebooks, and Wolfram language as the sort of glue. But there are many other slicings you could make to that. Let's talk a little bit about AI. I mean, there are many different definitions of AI. And again, I think people have slightly jumped down the idea that LLMs equals AI. That's not what I think of it as. I think LLMs are a great mechanism for achieving artificial intelligence. They are one mechanism that's performed very well on certain things, an incredibly interesting development. They're not the only mechanism. And it's sort of important not to forget everything came before. There's a precedent to this, which I remember, which is when, if you look at computing in many ways, right? So, people did things symbolically before computers. I mean, like somebody here will probably know much better than me, but I was always told that conformal mapping was used for Spitfire wings because you could do it, you could conformally map the wings and figure out some aerodynamic properties, and that was something you could do symbolically. Then when computers came along, it's much better to do it numerically because typically you can get wing shapes much better and optimize things by running fluid dynamic things numerically, etc. But then people completely forget about the previous method sometimes. And actually, the interplay between symbolic methods and numeric methods has been very powerful over the last few decades. But sometimes we've had trouble reminding people that you don't have to do everything numerically. That's not a requirement. Just because computers were fantastic for numerics and they managed to change a whole bunch of ways you do things, don't forget about the old thing. And so I think the same is slightly occurring with sort of AI. People ask me about Wolfram Alpha and how that relates to AI, so to speak. I mean, I think if we were relaunching Wolfram Alpha now, we would probably say it's an AI. But I would call it sort of symbolic AI rather than statistical AI. So we are deliberately trying to compute things as opposed to sort of statistically infer things. And that's sort of the mechanism by which we're trying to do it. And so there are places where that works very well. There are places where it doesn't. I mean, one way I put this is sometimes is to say, on the human spectrum, I guess ChatGPT or the like would be a sort of poetic end of the spectrum. It writes very nice stuff and communicates with other people very nicely. It's not always accurate. We're a more sort of a Aspergic end of the spectrum, where it's kind of like we maybe don't find it so easy to communicate with people, but we are fairly accurate and are fact-based, and we work things out very deliberately. So that's kind of what we're and the interplay between these, I think, has been a really interesting subject of the last couple of years. And, I mean, just to play, I don't want to see if this actually works.
Let's look at a short demo of what an intelligent AI research assistant could look like.
Let me just pull this along to actually show this.
It's also used a second tool to look up information.
Let's just see. Did that? did that come through to remote people? Am I sharing with sound?
To share the
sound.
that was.
Oh, some of these maybe, okay, so we haven't shared the, let me just go out of that and share, why don't I share my whole screen and put sound on? It does sharing sound, but not the whole screen. Okay, let's try that. Let's try this. So, I mean, maybe I won't touch with the sound, but let us, so this is a thing, you know, this is let's say a company which is got, it's trying to figure out the ingredient, you know, how to optimize, how to build a new peanut butter cup, for example. And the question is, can we
those
interplay
ingredients?
Between sort of...
In this case, they're common names, and put that together to give me an answer. It remembers the context of the conversation, so when I ask for their CO2 contributions, it knows what I mean, and knows that it can call another database of manufacturing data to get the information that I need.
Deliberate computational data and sort
of course, what I really want is to understand the combination of these ingredients in the context of my product. So when I ask for the emissions of the peanut butter cup, the assistant synthesizes some programming code, in this case multiplying the ingredients contributions by their quantities in the recipe and displaying that as an easy to understand picture.
Etc., etc. So you get the idea. But it's the kind of interplay between those that we've been trying to work out. I mean, here's another sort of a different example. And this is, let me see if I can make this a bit bigger. Let's see. And this is a much more traditional, you know, algebra thing. And just to show you the, let me see if I can just show you if this actually works. No, let me actually do it. So this is, we've got our own Wolfie persona. Gosh, I don't know why it is so incredibly fuzzified. Okay, well, let's not do that one then. For some reason, it's decided not to put its resolution to, I don't quite know what's happened there, but let's leave that. But so these are sort of early examples of combining those things. And one of the things we're trying to investigate is, so when you have something which is sort of fuzzy, like health, but you want precise answers, can you use this interplay to produce really good consumer-facing services that actually kind of work? And the problem people are finding right now with pure LLMs, although, you know, this improves at a rate of knots, is often that, you know, it sounds good, but then there are catastrophic errors. And the problem with us, where we couldn't quite get with like Wolfram Alpha, is that, you know, yeah, we can compute things, we can put lots of things in very deliberately, but faced with a real normal general member of the public, it doesn't quite get close enough to communicating with them that it can be a sort of free-flowing conversation, so to speak. So the fact that you can potentially put those together is pretty exciting, and that's some of what we've recently been trying to do. So, you know, obvious places, government services would be a very obvious place for that, but obviously there are many services just that anybody's offering. Okay, let me, I wanted to try and do a demo of stuff we've got coming up. This may be an absolute disaster, but we've been trying to build a very nice sort of setup for, let me try and get this up, see if this works. So what I would like to do here, this is the pre-release version of something. So if I had problems with, you know, normal software actually working in real time, I think this may be one level. As they say, if it's biology, it moves. If it's chemistry, it changes. And if it's physics, it doesn't work. I think demos of software go somewhere out to the far end of that. But let me try a couple of things. So what I want to do is show, I don't know, let me see if I can make this a little bigger. If I just utter something on the left-hand screen, what I wanted to try and do is build a piece of code for me from the utterance, which hopefully then will just work. And let's say, I don't know, something like make a program to show, I don't know, a live image, I don't know, from my webcam with my face blocked out by a rectangle, something like that. So what I'm hoping will happen, if the planets are all aligned, is that that's not a great start. Is that, let's try this again. Okay, let's try this. we going? Are we going? What's happening here? Okay, 2 + 2, that's 4. That's a good start. Let me get rid of, I tell you what I'm going to do. Let me just, I've had this bug. Let me try this, and let me try this again and see whether it actually reacts. Yes, okay, something's reacting. So it's taken that and it's munging on it. And we'll see whether it manages to write me a piece of code, and we'll see whether the code works and does the right thing, okay? All of which are open to querying at this time. So anyway, there we go. To create a piece of code, it's written what looks to me a slightly longer piece of code than it needs, but I'm not going to really pay any attention to that. I'm just going to try and run it, and we're going to see whether this actually does what I asked it to do. And oh, it seems to sort of be working. So there it is. It's blocking out my face, if it can see us. Okay, so let's see if it, there we go. And there's my face blocked out live from this, from a thing that I uttered to get a piece of code written that's now been written and is now kind of just running. There we go, in this. So that is a pretty amazing, I mean, you can see this in many languages potentially, but in whichever language and whatever you're doing, right, it's pretty amazing you can get that from an utterance and have a piece of code that runs. Almost sort of immediately. What's really nice with Wolfram language and where the optimization is, one of the problems with Wolfram language is we have, I think, 6,500 built-in functions. That's a very big language by traditional standards of languages. Now, the good news about that is we have things like, you'll see in this code, yes, there it is, find faces, which is just something that finds a face. So you don't have to write that. It's a nice systematically put in thing. You know, I mean, there's a lot of gunk here that possibly, I mean, I could just, by the way, while I'm doing this, I could say, can you make the code any simpler or shorter? Okay, I mean, I have no idea whether it'll actually achieve anything, but anyway, we can try. The nice optimization that we're potentially achieving here is, you know, so a difficulty with language is people have to potentially learn quite a lot of language in order to at least operate think that they're operating efficiently. I actually would question how much you really need to learn to operate reasonably efficiently. Obviously, LLMs don't care about how much language they need to learn. They're happy operating with many, many words. That's what they do well. And so that optimization is rather changed as against pure human interaction. So that's interesting. I wonder if this, I mean, again, I'm not paying attention. There we go. It actually works. It did shorten the code for me, amazingly. On second round, it picked, that's pretty much the code I think I would have written to achieve this. Nice short piece of code. And you see, it's nice. I mean, it's a very simple case. But it's nice that, you know, it's now I might decide I want to go into sort of abstract mode, if I can put it that way, and just rerun. Oh, it's obvious that if I change that to green, it should come up with a green box, right? Very obvious. But it's nice, this interplay between abstract code and, so to speak, human interaction with it. I think I could show a bunch of other examples, but I think I will quit while I'm ahead on that front. And by the way, lots of nice things when you pull in data and ask it to figure out. It is just, so there's a whole question around who can access programming, computer science, write codes, when you want abstract, actual, explicit abstract representation versus when you want to be uttering things. That whole business is going to be very interesting as we move forward. I do not agree with people who think that you can just sort of get rid of abstract code and somehow the world will be a better place and you can just sort of utter things and it'll just do what you want. I think that's not, there's a long history to where abstraction is useful in the world, from sort of, you know, money to program code. I don't think abstraction is going away as an explicit useful thing, but I think the interface there is much different. I think you'll often be editing things that are being set up for you rather than writing code from scratch. So I just want to take a few minutes to go from what we've been trying to do in computing and sort of the machine to a thing that I've been trying to work out, which is what should change for humans in this new world. What should humans differently learn, given that we now are moving into this new era, which I would call the AI age? So, for want of a better description, I kind of think that in the same way as people need to be kind of literate, they need to read and write, people need to have, everyone in society needs some kind of computational literacy, an ability to understand how to think in this sort of maths computational process, if I can put it that way. The words are quite hard to come up with here because they're quite polarizing. And at the top end of this is people like you who have very, gone to a very high level in trying to use computational thinking to achieve, many different things explicitly or implicitly. But it is very critical that for our societies, we do actually have everyone with some basic underlying understanding. And I would sort of compare this a little bit, if you think about literacy, I think, so the idea of maths literacy, I think, is sort of, largely a late 18th century type of thing. There are a lot of people who said, the aristocrats and the high priests and things, they can read and write, and most society can't, don't need to, too stupid to, whatever the thing is. And I do think that the fact that most people can read and write, it's been a very significant, probably the most significant single idea in sort of education and mass education in that sense. So I think there is a sort of parallel to some extent now with, can everyone understand how these decisions are taken? We're being told about decisions, all of which are taken with some sort of computational decision-making element. Most people are completely ill-equipped to understand anything about how that's arisen. And you see some of the consequences of this in different democracies where people are saying, some expert came on, the expert talked garbage, but said that they could predict there would be this number of, deaths from COVID, or this thing would happen in this way to a precision that didn't seem real. It didn't play out that way. So then maybe all experts are talking garbage because I can't tell between them because I don't really understand anything about how they're thinking about this. So that's the kind of problem I think you end up with if you have no mass not understanding this. So where is this in our mainstream education in schools? Kind of hard to find. You'd hope the mainstream computational subject is maths. And it's been added to by computer science as it's not mainstream in the same way, but it's there, and in the UK has been reasonably ahead on trying to do that. So a thing I've been on for a long time is if you look at, let's say, A-level maths, I think for what it's claiming to try and achieve, it's pretty much 80% the wrong subject at this point. It's a subject of how you hand compute a very small number of algorithms that were historically what you would have used for a bunch of things, mostly around sort of physics and accountancy, right? That is not what we're using mathematics or computation, whatever you want to call it, generally for now, and it's not how we're using it. So if you want most people to understand what the hell's going on, this isn't going to do it. And actually, it's got worse than that, because as it's got more important to do, let's say, A-level maths, it's also got more procedural, because more people are sort of, the handle is turned for more people. And so it's, in fact, kind of got less meaning, and including for the people who want to the high end, who are actually very interested in the maths itself, which is a small percentage of the people, important, but small. And it's not actually that useful for everybody else. So if I was to summarize the problem, in real world maths, computers do almost all the calculating, and in educational maths, people do almost all the calculating, and there's the problem right there. And it doesn't matter how well you teach the wrong subject, it doesn't really make it right. And if you look at what, I don't know, you can write down what is this maths computation process we've been talking about, this sort of magical process that's so powerful. I would argue it's sort of a four-step process in which you define the problem. If this room has no ventilation, we lock all doors, it's airtight, and I speak for too long, how long could we survive? That would be a definitional problem. I would then abstract that into maybe an expression. And that's a sort of magic, abstraction. There's a power to the subtraction, because we can take lots of different scenarios and put them into the same abstract expression that we've worked out how to do the magical step 3 from, which is to take the question in abstract form and turn it into the answer in abstract form. Hundreds of years of experience of that, and now fantastic machinery for doing it very quickly. And then you interpret the result. It's, x equals 3. So does that mean 3 hours? Or if it came out as -2, it was probably wrong. And maybe I need to go back and look at this again. And what's happening in our mainstream education is basically all the time's being spent on fairly trivial hand calculating problems. And we're not spending any time on the other stuff, which we critically need, because as the things get fuzzier and harder and the uses of mathematics in the real world apparently get more distant from the abstraction, people get more and more confused. And so we need computers much more for, we need to use computers for step 3 most of the time, and we need to use humans much more for steps 1, 2, and 4. And then, of course, we've got AIs. And AIs are blurring this even further, because whereas I would have said up to a few years ago, almost all of steps 1, 2, and 4 were very human at this point, that's not quite so true, as we just saw. I mean, quite a lot of what I was doing there was I was basically trying to define something sort of in step 1, and it was taking it and doing the abstraction for me in step 2, and potentially even doing some interpretation. And so, you know, another way to think about this is you're going through these 4 steps, and you are looping round through these. You may be doing it very quickly for a simple problem, or you may take years on it for a complicated problem, and eventually you decide you've got a good enough solution. But you've got to learn how to check your own thing as well, and understand how to interpret results. So here's a typical thing that, you know, we like to set, which would not be in a traditional A-level maths thing, which is if you, let's say, take a class and you divide half the class, you know, take half the class, tell them to toss a coin and write down the results in reality, and you take the other half and you tell them to, you know, just cheat by typing heads and tails into the computer. And you look at the results, say from 200 coin tosses, can you typically tell who's cheated and who hasn't? And the answer is pretty reliably yes, unless they know what they're doing, right? So in this case, there were 5 tests we ran on it, and it passed 1 test and failed on the other 4. And if you do it in reality, it pretty much typically passes the 5 tests, okay? So it's very interesting to the average, you know, 16-year-old who hasn't seen this kind of thing before. How did it know that? How did the teacher know I was cheating? And then you get into, you know, discussions about sequences of data and so forth. And, you know, how does credit card fraud detection work? Simple things like that, and sort of view into that. And, you know, it turns out that most people type too evenly. They think they actually, in reality, when you toss a coin, you know, you get quite long runs of heads and of tails and things like that. And when you type it like this, most people don't do that unless you know what you're doing. That's how you can tell. I mean, a very simplistic way of telling that. So that's a kind of thinking pattern that just isn't in maths education anywhere right now, really. Not normal A-level maths education type thing. It's a very simple thing. And again, you can't really do this stuff without a computer, because it's dependent on this way in which you deploy mathematics and computation is dependent on having a machine that does these things for many of these sort of algorithms. So if you remove the computer from education, you will remove most of the modern context of the use of mathematics and computation, because it didn't exist. People didn't use it for medicine and biological analysis. Too messy. Nothing really got, I mean, you know, certain, you know, basic things got done, but nothing like what one would do now, because it couldn't be done before you had the machines that would do it. So therefore, you can't do that as a real context in education if you strip out the machinery that allows it to be done in real life. And so what ends up happening is people often learn a different computational tool set. Like, where is machine learning in the A-level curriculum? Don't think it made it in. That seems a problem. I mean, certainly not in maths. Seems like a major sort of way of working things out these days. Why wouldn't it be that? And you actually end up with a lot of the wrong stuff. In fact, you end up with, even worse than that, in my view, you end up with people who can't interpret messy problems because they're used to interpreting it by doing it by hand, or running a very simple process on which doesn't mesh with how you'd actually do things in real life now. So you actually get really horrific problems. And, you know, you can trace little bits of the 2008 financial crash to people fitting completely the wrong distributions and all sorts of things like that. They shouldn't be using distributions half the time anyway. And so another way to think about this, which is quite interesting, is the cost-benefit analysis of the 4 steps has dramatically changed. So the expensive step was step 3 for hundreds of years. It was very hard to compute things. That's what you spent all your time as a human learning how to do. so that you could use mathematics to do the things you could do. Mostly that's now very cheap. And the other steps are much more expensive, and we then do much harder things, and we then get confused. Actually, a rather nice anecdote is I was lucky enough to have a teacher at school who was had been a friend of Alan Turing's, a fairly eccentric maths teacher. He used to say maths is the art of avoiding calculation, about which he was very correct at the time. But that's been turned on its head. So anyway, we've been trying to think about how would you build a core computational curriculum that assumes computers exist at the outset? What would be changed about that? What would you study? How would you study it? How would you get people to a much higher level for the things they really need? If they get very interested in what's inside and they really want to become mathematicians, that's wonderful. But that's not probably where you start for most people, et cetera, et cetera. So that's sort of, and you can look at, we've been sort of building, I mean, so this is an example where we built, how fast would you cycle a stage in, I don't know, the Tour de France? How would you embed, I don't know, air resistance? Where would that be different? You wouldn't normally face these sorts of things at sort of A level, but if you're just using things to do this, you can go much further and faster in concepts. So you're sort of not bound by computational complexity, you're bound by conceptual complexity. And let me see, so here, maybe rather than do this live, let me just try and, what's exciting here is now when you try and get an AI to tutor you in this, I'm just going to make this a bit bigger if I can. Let me just increase the magnification. Okay, so I wanted to set myself a little project of trying to get coached in how would I think computation about, how should I fly or drive from Oxford to Inverness? And so it's quite entertaining just to see, what a fairly simple persona we put together using this sort of architecture comes back with. Great, well, there are some things you should think about. What's the distance? Would you care about cost, or do you care about time, et cetera, et cetera, et cetera? And, I say, well, 2 is what I really I care about, cost and duration, whatever it is. Then it sort of helps me think about things. Then I do a little calculation myself, and I try and estimate, and I try and explain my estimation to it. Then it comes back and throws some other things at me. But then I remind it that actually, I've got to remember about parking at the airport, which costs something too, et cetera, et cetera, et cetera. And then I throw in another thing that at some point in the last few years, I got a private pilot's license. So there's another option. And it then kind of runs with that option. I explain how much it costs per hour. And it then says, well, that there are other options here, et cetera, et cetera. So, it's fairly basic. But it is a very interesting move forward, because I think it means that you can potentially implement something like this where there are not, necessarily teachers who can coach this very easily and things at the outset. So if you can do this, I think you end up with a much better range of outcomes for the human. And, I think we tried to put together a list of such outcomes, including like, I don't know, confidence to tackle new problems and things like that, which really are very important, how you communicate and collaborate. And there are really ways we can help humans with this. They're not just black boxes. And I think it's really important to actually think about what one's doing there. And the other amazing thing about curricula, if you've ever looked at them, is that they go into minutiae very quickly. It's kind of like, what is it you're trying to achieve out of maths, computer science, whatever it is? And it kind of goes to these minutiae of kind of like, well, they need to know how to put, labels on bar charts. It's like, okay, or they need to be good at thinking critically. But what does this mean? So you need something that actually explicitly talks about ways to think, like the process I showed, and you need to really engender that. And that's why I wrote the Maths Fix book. I left a copy at the back, which is trying to lay out what I'm proposing should actually be done here and where one could actually fix this. And I'm pleased to say we are finally, not in this country, I'm sorry to say, but in other countries, finally actually getting some take-up where people are understanding there is a way we could reform this, and we could do much, much better, and it would really help both our societies in general and also the top end of this, I think, as well. So we kind of need to decide, as we're going forward, what is for the human and what's for the computer, so we humans stay on top. And that's not a particularly, easy thing to figure out. And we kind of want sort of first-rate human problem solvers, not third-rate human computers. So don't pick what the machine's good at and try and get humans to sort of simulate that. Why don't we just step above a level up, which is what's happened in all previous industrial revolutions, at least well, I say it's happened. People who've succeeded, societies that have succeeded, have stepped on top of the machinery and gone further. Societies that have tried to compete with the machinery have basically gone backwards. And there's always a lot of dislocation in industrial revolutions, but I think that's the way one has to think about it. And obviously, education is absolutely critical to that. But one of the most exciting things about this revolution is you can get the machines in the educational process. Like if you were in the previous industrial revolution and you want to build a smelting plant, you can't kind of take the smelting plant and put it in the classroom. Right? You can take a computer like I'm using industrially and put it in a classroom. It's pretty much the same object, and you can do all these things. So that's a big difference from some of the previous sort of industrial revolutions. So anyway, amongst other things, I would like to see a much better enfranchisement across society. This computational divide I think we've got is a really important thing to solve. And as I mentioned, this sort of mass literacy and mass computational literacy. I thought I would finish with a few minor anecdotes from the last 36 years or so on the computational front line. Just some, and the first ones revolve around Steve Jobs, who was at our release event, Mathematica, in 1988. In fact, he came up with the name Mathematica, and very Jobsian sort of name. And this was a quote I found recently, rather relevant to what I was just saying. Mathematica will revolutionize the teaching and learning of math by focusing on the prose of mathematics without getting lost in the grammar, which I think is a very nice quote. The reason he was at our release event is because we were bundled on Next machines, and I think that's the first of which is in, I believe, is in the Science Museum. I mean, the mission, not the first of which, the one on which the web was first put up. But by Tim Berners-Lee, and I think that is the actual machine in the Science Museum. Anyway, we were bundled on that, which is how we ended up doing that. And I thought if you wanted a little piece of history, I dug up. This was a video sent to us for our 10th year anniversary conference by Jobs. And Jobs at that time had just, I think Next had kind of declined, and he'd just been rehired at Apple, and Apple was in an absolutely disastrous state, right? It was sort of, months away from bankruptcy. And it's quite interesting to hear what he has to say.
Stephen, congratulations on 10 great years of Mathematica. Having seen it from the start, having had a chance to work with you while you were developing it, having the first version be on the Macintosh and doing a great version on Next Step together, it's been a great ride. And Mathematica's changed everything. It's in use in every major university, in most major corporations. And one thing we're really excited about here at Apple is that just as Apple is re-entering the consumer market with a vengeance with iMac, you guys are going to be coming out with some versions of Mathematica for consumers and for K-12. And we are super excited about working with you to make the next 10 years of Mathematica even more successful than the first. So happy anniversary. Congratulations.
So it's an amusing mark in history, in particular, where it says, we're going to the consumer market with a vengeance. Well, he was right about that. This was another anecdote, which was a guy called Michael Foale, who's a British-American astronaut who ended up on the Mir space station. And I'm afraid rather thematically, this has a good ending. So rather thematic, I believe the story of this, if I've got it correct, is that the Russians decided they wouldn't pay for Ukrainian radar guidance system to guide in the supply ship. And so the poor cosmonaut inside the Mir space station had to try and manually guide in the supply ship, which he had never practiced. And it crashed into the space station and made a hole in it. And so they were spinning, out of control, basically. And they had to go around and basically seal everything that seemed to be leaking. But they survived. And then the problem was, it had a great design that the solar panels, its batteries were degenerate. And so if it was spinning, it couldn't get gyro power. So its solar panels were rotating away from the sun, and so they couldn't therefore stabilize it. So they had escape thing which had rocket boosters, and so they tried to work out what to boost in order to get it back in shape. Anyway, we discovered all of this because unfortunately we had the next supply thing, a new module and things was sent up, and I forget the whole detail of this, but we got a customer service call saying we'd like a new activation code. And we said, well, what's the reason for this? Oh, well, the original copy is lost in space. And this actually turned out really to be true, right? The machine that Michael had was in one of the bits they'd have to close off, and et cetera, et cetera. So anyway, he was trying to use the equations he'd learned at Cambridge in Mathematica to try and work out what to boost in which direction. Anyway, had a happy ending, and it came back. But that was so we found out the details of that, and we've had various weird things along the way. This was a poster, as you can see, quite long, of the Riemann zeta function along its critical line that for some reason we decided was a very good idea at some point. And this was another thing that existed many years ago, which was, there were two of them actually, the Mathmobile, which went around various places and universities. And this was the American one, as you can probably tell. There was a British European one. And one of our interview questions is, the Mathmobile arrives at a walled European city, and the gate is too small to get through. What do you do about organizing the event? And this really happened. I think it was a Porto in Portugal, I believe. Anyway, and we've had various different logos, and you'll see the Wolfram Alpha logo is a rhombic hexacontohedron, which is, I had fun asking somebody, a friend of mine who got the top first in grades and classics here in Oxford, how many sides it had. So I reckoned if he couldn't figure out how many sides a rhombic hexacontohedron had from his classical education, then we were in trouble. Anyway, I think he did get it right, which is 60. And this first appears in the literature, I believe, for a German mathematician in 1942, working in Germany, indeed. So anyway, it seems a rather, not simple, but sort of shape you'd have expected to appear before 1942. But anyway, so I think I will just end there by saying, I think we're only just entering the computational era, and we've got a lot more to go as we, even now finding electricity, more things are happening with electricity. I think we'll be going at this for many, many years to come. Thanks very much.
Well, thank you very much, Conrad, for absolutely fascinating talk. I think you said you're willing to take some questions.
Yeah.
So if we have any questions online, can you please put them in the Q&A on Zoom? Not the chat, the Q&A, and I will pick those up and ask them on your behalf from here. I'm going to start off with an audience question, and I'm going to pass the microphone round.
Can I ask about your 4 stages of define, abstract, compute, and interpret? Where does problem solving or design come into that process? Because there are going to be problems where you may have a clear specification, but no idea how to actually design it. Like if you ask the computer, could you give me the proof of the why there are infinitely many twin primes, it would presumably have difficulty.
So I mean, I count the whole. So I count the whole thing as the problem-solving process, and it may be that you don't very explicitly go through all the steps in that mode, so to speak, to do it. But I think if you look at what you're actually doing in that problem-solving, trying to produce a proof, for example, you may be going through that process in multiple times in different parts of doing that. So I mean, I don't. The way I look at this is, in practice, one is explicitly or implicitly running something like that process. And that is, in a sense, what's made mathematics so powerful. There is an underlying process that one can run to get answers. In terms of sort of each of those steps, if you like, you could break into other steps and are highly creative potentially in order to get to the next step, if I can put it that way. So, I mean, the reason I lay that out is because I think there are several groups to it. There are people who think what one's talking about with computation is it's kind of a piece of magic that just sort of happens, which I think is wrong. Just the way I think if you ask a poet, how do you make a poem? If you really break it down, there are steps that poets go through. Now, when they become very good poets, they don't necessarily explicitly learn or think about those things. And I think when you become very sort of used to or experienced with computation, you're not necessarily going through kind of each step very deliberately. But I think for many people, some people who are learning it just naturally see how to do it, and that's wonderful, and they don't need to explicitly look at these. For most people learning how to think about, let's say, setting up a proof, I think it's really helpful for them at least to think through this way of doing it, certainly if they're lost. So that's, in a sense, I don't want to make them sort of some sacrosanct thing, but I think it's sort of helpful to think along those lines. Maybe you disagree with that way of looking at it.
I don't think you've answered the question.
Okay, so repeat the question, see if I can try again.
Of the four parts, define, abstract, compute, interpret, does problem solving or design come in?
I think it's the other way around, it's the inversion of that. I think problem solving is the whole thing. I think those are steps of problem solving, is what I'm saying. And design is, I mean, each piece has design in it, but it depends which bit you're designing. You might be designing, so for example, designing what you abstract to. It's a very complicated problem. So I've got a problem. If you think about it in coding terms, you know, how am I extracting? I mean, there are various ways I can describe this problem in an abstract way. So to me, that particular piece of design, if you like, is how you go from step 1 to step 2. And it's an absolutely critical thing. And you know, many things that relate to that, you know, like the language. Which language are you going to? Do you think a different way if you're used to using C++ or assembly language or Wolfram language? Do you think a different way about what you're doing there? I think the answer is yes. I think it's a bit like human language in that sense. I think there's a slightly different take if your first language is, you know, one type of language from another type. It tends to cause a different sort of thinking. So I suppose my answer is, okay, let me try again, round 2 answer, is, you know, I think there's design at each piece of this. There's design when you've decided how to abstract it, about the detail of how you actually write that down and do it yourself or get a computer to do it. You know, there's ways in which you'd not only interpret it, but also verify it, which has a design to it. So there's design of the whole sequence of things at a large scale. There's a design at a smaller scale of what you're doing, I think. The problem solving is the whole thing, but there are bits of problem solving in each element of that too. I mean, that's the way I look at it. And I think there's nothing wrong with looking at these things, you know, the transpose of this in some sense at all. I just think it's useful, and so that, you know, I'm all for saying, right, what is problem solving? What do we mean by problem solving? How are we doing it? I just think it's good to look at it both ways around. And it's strange to me that if you ask most people with a basic mathematical education, you know, what are you doing? What's the process you're following? If you just deliberately want to do something, they haven't got the foggiest idea. And one of the mistakes, by the way, I think, just to round this out is, you know, in many other walks of life, when you're doing something, particularly under high pressure, you're taught to fall back on a process when you don't quite know what to do, which I think is quite useful. Certainly in the military, that's very prevalent. I don't understand why we don't get people help with process early on. Like, you know, if you say, I've got 12 sweets and I want to divide them between 4 friends, you know, I want to fairly divide them between, I want to give my friends fairly these 4 sweets. Well, the first question when you define the problem, what's fairly, right? It may not be that it equally may not equal fairly, depending on what your friends are like. But the point is, you know, that's step 1, defining the problem. You know, step 2 is abstracting that to a division sum. Step 3 is computing the division. Step 4 is interpreting that makes sense. If I had 11 sweets and it's 4 friends, can you divide the sweets? Does that make sense? Does it not make sense? So obviously at that stage, you don't really need to break it down like that. But I think when people later fall down in their education and they say, oh my God, I'm panicked, I can't figure out how to do this, they have no idea where they are in that process. I think knowing where they are, if they're not sort of natural mathematicians, can be quite helpful to them. That's, you know, another part. I don't know if that answered it. Okay.
I'm going to ask one from online. It's quite long, from David Bauer. Taking the analogy of electricity versus computational as accepted, my level of understanding of electricity can be extremely low to utilize the beneficial effects of electricity. I just plug something in that I bought from the shop and it works. Mm-hmm. Why is the level of understanding for computation needed to be much higher? Is it just the case that we're not as mature at computation as we are with electricity, or something else? I'm coming from a point where education is valuable, but agreed that the current content is not optimal. Is it important that virtually everyone needs to understand the wonders of Pythagoras to pass GCSE maths?
Yeah, it's a great question. Great question, which is, the driver versus the automotive engineer kind of question. And I think it's really well put. I think there are elements of the use of computation that will be as simple as electricity now feels. But that's by the time you've got many, many, many layers of sort of automation and utility on top, which we're starting to get. I mean, what you're doing is a bit different. It's not a complete, I mean, as with all analogies, it's not a great, don't take it as a complete perfect mapping. I mean, obviously, one of the things that's the case for sort of computational things and AI stuff is that it's sort of somehow it feels very quintessentially, maybe all industrial revolutions did, but this one feels very quintessentially human in the sense that, humans sort of believe they're marked out largely by intelligence. And obviously, this seems where machine has impinged on that core capability, so to speak. So I don't know whether, so I mean, the extent to which it will be as straightforward as plugging something in, I don't know. But I think that a very important thing to understand is the difference between the users. Early on in any technology, the users and the builders are often quite similar, right? I mean, so, cars 150 years ago, the people who drove the cars were largely people who were certainly involved in, fixing them, but possibly engineering them as well to a large extent. Obviously now that's totally different because it's got much more advanced how you build them. There's a very small number of people who do that. There's a much larger number of people who drive them. And I feel like it's the same thing in computation. We've been in an era where a small number of people engineer it, and mostly, to a large extent, at least a few decades ago, they were the people who used it. Now, a lot of people are using it to some extent, but it's a bit lumpy. The user interface is not always great. But, if you have a high-performance car, it's sort of important not to just know how to drive a horse and carriage. It has different things you need to know about operating the machinery so you don't get into trouble. And so there's several things you need to learn. So one of the ways I put this is you need to learn that there's a difference between the essence of what you're trying to learn and the machinery of the moment. Another analogy I would draw is, photography, still photography, for example, when I enjoyed doing as a kid, I mean, as I say, if photography was a mainstream subject now in schools, I think the first lesson would be how to load a film into a camera. Because people would have got muddled up between the mechanics, which you needed to know. I mean, when I was doing photography as a kid, you need to know how to load a film to camera, otherwise you couldn't take pictures. But you need to know the mechanics at that moment of what to do, because otherwise you can't use, you can't make progress. Same now, you need to know stuff about how to program, how to operate a computer, otherwise you can't function. But that isn't the essence of computational thinking. That's the particular mechanics of the moment. And one of the things we need to make sure is we keep in our heads what the essence is. And the essence evolves, but we don't get locked into a particular mechanics of the moment, which then changes and we get different mechanics. We need to then jump to the new mechanics and use the most modern thing typically that works. So I think to answer the question, there will be a lot further to go. And I think the LLM revolution will help a lot. So this bridge I talked about will help a lot to get much more everyday use of computation, but there are dangers with that too. So I think there's, in the direction of electricity. And in terms of what you need to learn, do you need to learn details Pythagoras? This is what we've been trying to work out. It's really hard to know. What do you need to learn in order not to get fooled and to make optimal use of computation, but not necessarily be the people who actually build the next round of it? What do you need to know to drive a car effectively about the mechanics of the car? Well, there are some things you need to know, but they're different and they diverge more the more automated it gets. If you're a Formula One driver, you need to know quite a lot more about it because you're on the edge of what the machinery does than a normal driver, et cetera, et cetera. So there are all these different things. So my argument basically is you should start from the usage for most people. Hopefully, actually, a larger number of those get interested in what's inside and actually end up being the people who would like to build the thing as well.
Oh, thank you for that. There's a lovely quote by a geographer called Suey, who I don't know much about, but he said, thanks to powerful computing facilities, as a society, we have become data rich, information poor, knowledge starved, and intelligence devoid. Do you think this is still true, and do you think it's going to get better or worse?
Yeah, it's very hard to, I mean, I'm basically optimistic, right? I mean, I think that's, I suppose, the generalization. But I mean, look, as with all major technological revolutions, there are individuals who win and lose. There are things that get a lot worse. I mean, you know, certain kinds of crime that, you know, win for time. But overall, I think that we're already gaining quite a lot, you know, in terms of what you think life is for, right? But in the end, you know, richness of life because of modern, you know, information and data, I would say, is on the whole greater, right? Yeah, I mean, I think one of the problems at the moment, I mean, every industrial revolution has problems, right? I think one of the issues at the moment is it's so, things happen so quickly and it's so sort of globalized in what happens that you get these very quick buildups of issues which, you know, percolate through. And obviously we've seen social media be an issue in all sorts of ways. The thing about sort of information, you know, data rich and information poor, whatever, if that's the right way around. Yeah, I mean, that's true. I mean, we've had, I mean, it's actually a subject of a talk. You know, a talk I sometimes give is something along the lines of, you know, has massively more data led to better decisions? Well, no, you know, that's not as much, certainly not as much as it should have done, right? And it's fairly questionable. And so there are funny edges to this. So for example, and this is an edge that I'm very worried about in our education. So numbers have a fantastic marketing appeal, like to governments, you know, to people putting road signs up, this sort of thing, right? And so if you can peg some outcome to a number, you can get people persuaded often that that's the thing you ought to optimize for. But of course, as we all know, the numbers can be highly simplistic of the representation, you know, of representing what we actually want to achieve. And so one of the mistakes I think has been happening recently as a typical outcome of this sort of mass modeling and data science and everything else is that very complex effects, you know, environmental effects or big scale things, people do some modeling, which is maybe pretty inaccurate anyway, but let's say that the modeling of the primary effect has some validity, for argument's sake. But I think what's going on is if in the past they'd literally not had any mathematics, you know, they just thought about the problems qualitatively, I think they would have balanced sort of primary, secondary, tertiary effects much better than they do now. So now they jump to one effect, which they've managed to model, probably not very well, but let's say they, you know, and they completely obliterate the other effects from their heads. And so I think that's pretty dangerous, and that's a sort of negative thing. Now, I think as people get more experience, they will, I mean, as society gets more experience, hopefully we get better education, that will improve. But that's a kind of error that I think occurs. I mean, you know, I don't know, you can cite many things, you know, let's, I probably shouldn't be too political, but I mean, let's shut off all the nuclear power stations in Germany because it's safer. Okay, that hasn't had particularly good consequences in my view over the last, you know, recent years, right? There are all sorts of secondary effects of that, which you need to think about hard before you decide that that was the right course of action. It's a complicated thing. Don't just model that. Don't just think about that. So that's a type of thing that I worry about.
Thank you. So education is a moving target, as you said. But if you take right now, if you're saying that focusing on the primary, secondary, and A level, what would you say should be the sort of minimum thing they should learn in terms of calculation in primary, secondary, and A level now?
Yeah, I mean, what should they learn in terms of calculation? I mean, so it's sort of slightly hard to answer in the abstract. I mean, I suppose I have a couple of tests I would do of any part of the curriculum as to whether it's worth it or not, with respect to learning sort of whether you need to know the insides and how to do it by hand. So one test would be, do you do it that way in real life now? So a question I'm often asked about is times tables. Is it worth learning on times tables? Okay, I mean, I think it's still quite useful because although I could type the thing into my my phone and do the multiplication, I still often in my head many times a day multiply things together, and it's useful to know that 5 times 6 is roughly 30, right? Is that some terribly exciting pinnacle of learning your stuff in primary maths? No. And frankly, much more important is that you know when you'd use multiplication nowadays than the fact that you can actually do 5 times 6 quickly. But would I leave it in? Yes, I would leave it in. Long division. No, I mean formal long division. When does anyone ever use this? What does it teach the average person? Zilch. I think it should be out. So I think there are tests you can run. Now, if you talk about, let's say, calculus, you see, I don't understand why we don't teach what the idea of calculus and using it to 10-year-olds. Don't get it. I mean, to me, the idea of, take some shape, slice it in little cylinders and add up the cylinders to work out its volume or something like that, and there's this magic function called integrate that can do this. That seems actually a thing that's quite easy to grasp quite early on. But we don't do that. The reason we don't do that now is because you need to get to a good hand algebraic capability to be able to do integrals. So we leave it until, A level or beyond. So we've got all these weird, so it's a complicated question as to what do you need to learn by hand? What do you need to learn about it? Like what do you need to learn about equations? Well, there's the idea of an equation as a sort of mechanism of computing things. Pretty useful idea. There's, explicitly what you do with a quadratic to solve, very few things come out as quadratics, but yet we spend a lot of time people learning how to solve quadratics. It doesn't seem that useful to me. I'd much prefer them using differential equations much earlier, even if they don't know how to hand solve differential equations, as long as they understand the concept of a derivative. So I suppose my tests are, do you use in real life? Is it conceptually empowering to learn how to do it by hand? Now, to some extent, there's some conceptual empowerment, but is it worth it? So for example, in an equation solving thing, I think knowing that you're trying to balance both sides of the equation by what you do is sort of useful to know in a simple level. I wouldn't practice it to death. But the reality is, for many years when I had, x plus 2 equals 4, I knew you moved the 2 to the right-hand side of the equation and changed its sign. That's what I kind of knew about it as a thing, which wasn't really particularly conceptually empowering to me. So I think we need to focus much more on a very few things that would help people to really grasp what's going on. And we've got to be honest about that. And there are actually quite few of them relative to what we think there are for that level. And then I think we've got to, take them further and faster on conceptual things. And in practice, I think, early primary right now isn't too bad with respect to this. By the time you get to late primary, a lot of people are losing it because they get all this abstract stuff. They don't understand why they're doing it. There's no context that they care about. And unless they're interested in it itself, which is a very small fraction, they lose it. And the pity of it is the people who are interested in it itself, the maths, the computing, the actual thing, get bored rigid most of the time because it's not hard enough for them. So you kind of get neither, you're between two stools often with what happens. So that's a rough cut, but the detail matters in each of the things one's looking at, I think, as to what you really need to learn.
So I'll ask, first of all, thank you very much for very interesting ideas on the maths curriculum. How would you alter the computer science curriculum?
I know slightly less about that, though I've had very nice conversation with, for example, Simon Peyton-Jones on this topic. Well, look, the first thing to say is it's nice that there is one back, right? And that isn't just, how to learn Excel or something, right? So the fact that it exists and the fact that that suddenly got pushed in is actually interesting in how it got done as well. So that's step one. Look, the one thing I think some of it seems quite good. I think that I worry that we're slightly the same problem as maths in the following sense, that I think that it appeals to some people already excited about that and doesn't appeal to people who might be excited about some of the things in it. But somehow it's sort of the people who are already into programming and things like that. And so it's sort of, I feel it could attract people more by context possibly than it does. I mean, in a sense, what I would love to see as a mainstream subject is some funny mix of what I'm, the maths, sort of computer science, and this computational thinking, which I think very much mesh together as a mainstream thing, which would give people context. They would absolutely be programming things because, I mean, if you're talking about step 2, abstraction, I mean, how you write that down? Well, I mean, very few people write that down with nice squiggly symbols of 200 years ago, right? I mean, you write it down as code. And so being able to abstract, and obviously code is, I suppose traditional maths is good with, it was an early programming language, good for expressions, but not very good for process. And so actually that much broader canvas of abstracting to process as well as it is really important as part of that thinking, because as we were talking about earlier, you want to have a broad thing to abstract to. So, I mean, the real thing I would love to do is see one combined thing as the mainstream thing that at least encapsulates a lot of this. And obviously there can be more specialist maths and computer science people who really are excited about those things in their own right. I suppose that would be what I'd love to see. I mean, I do think the maths thing will break. I think we're on a course like Latin was. And I don't know quite how that's going to unfurl. It's getting, and the years I've watched this, it's got closer. I mean, people think it's unassailable, but that's what the classicists thought in sort of the 1950s. And they were wrong. I mean, it was a slightly more select group and everything else. But I mean, the idea that to go to Oxford, you had to have a Latin A-level, regardless of what it was you wanted to study at Oxford, was pretty nuts, right? And we're slightly in that way with maths right now. You have to have a maths A-level, do all sorts of things that don't seem to have anything to do with a maths A-level. There's a sort of Markov thing. So anyway, the main thing is though, and Britain was quite far ahead in this, and one of the arguments to the government here is, it's a real shame that, I mean, that there are actually a lot of things that would allow Britain to be quite far ahead in reforming maths in the sort of way we're talking about. And there are quite a lot of things they're like. We have a fair number of computers in schools, and we have the computer science thing that's obviously fewer people in the maths, but it's there, and it's got a good following. We've got a population actually who would be quite amenable to a change. That's not true in all countries. In the US, there are all sorts of funny problems because there's a sort of complete bifurcation between people who think, yep, everything should be changed, it would be great, and nope, it was written in the scriptures and that's the way it is, right? And there's not much in between. And in other parts of the world, there are other weird problems. Actually, in Britain, I don't think this would be particularly hard to get the public on board with some effort. So it's sort of the other way around problem. So it's a slight shame that we can't seem to move this bar in Britain. And I hope there's some way to put what's happened successfully with computer science together to make this. Anyway, so those are a few musings on it at any rate. Great.
Well, thank you very much, Conrad. We're going to have to call it a day there, I'm afraid. I know there were 1 or 2 hands up, but perhaps you might want to come and just quickly ask Conrad at the end, but we do have to vacate the room. As a former mathematician, I guess I'm still a mathematician because you probably always are once you started being one.
Embedded,
one thing I'd like is all those hours back that I spent learning how to do log tables when I could have gone out and bought a calculator. In fact, I owned a calculator and I was still doing log tables. And I think people should learn calculus so they know that when the rate of inflation is going down, that prices are still going up.
Yes.
And I think the pandemic showed us that people need to understand what exponential growth is and what the implications of it are, because I don't think I heard in the whole of the pandemic, I don't think I heard anyone explain it properly. And it's not that hard to explain. So I'm with you on what you're saying. Thank you very much for your explanations this evening. And I'd like to thank you as usual with another round of applause. Thank you.
Thanks.